Welcome to this workshop on simulating wireless control. In this video we will examine the solution to the workshop in Chapter 11 of the book Wireless Control Foundation. In this workshop we go through a number of exercises that demonstrate how simulation of the process and communication can be implemented easily in most DCS systems. The example we'll use in this workshop is a recycle tank simulation. In the first part of the workshop, we'll examine the module that is used to create the simulation of the process and the communication. We'll examine the composites that are used in the simulation for wireless communication as well as process simulation, and look at those in both an online and offline mode of operation. We'll then examine the simulation of the control and the process, and then adjust the pump out of our recycle tank to demonstrate its impact on the communication as well as the process. We'll then introduce a change in the recycle flow. In this exercise, then, we're simulating a recycle tank in which the inlet flow to the tank is a makeup that is adjusted with an on-off wireless valve, so the control is adjusting that based upon a wireless level measurement. The other input to our tank is a recycle flow that's an unmeasured disturbance to our process. The output of our flow is regulated through a wired throttling valve. The measurement of flow, though, is a wireless measurement, and so we're using PID Plus to regulate our throttling valve to maintain a flow target set point on the pump out. The makeup flow and the outlet flow valve positions then are the input to our simulation, are used to calculate the level of our tank and the flow out of our tank. The recycle flow is just an unmeasured disturbance in our process simulation. This is the module that we've created to simulate the process as well as the wireless communication. The input, as you notice, are the two valve positions. Based upon the makeup flow and the pump out flow and the recycle flow, then we're calculating the level of our tank, and that becomes an input then to our measurement of level, and the simulation of flow becomes the input to our simulation of the flow in. The wireless communication is demonstrated here. For the wireless communication to our on-off valve, there's a delay in the communication getting to our valve, and then the response and that response getting back to the control. The simulation of that wireless communication to our on-off valve is shown here. If we detect that we have initiated a change in the valve, that is, we're in this active state 1, then we wait for the communication delay before the actual change is used in the process. Once we have made the change, then we wait for the response delay before we allow another change in the output, and that is what is shown here in terms of the simulation. As you can see, that can be implemented very easily in most DCS systems. The flow into and out of the tank is simulated using a similar composite in which we take the valve position, multiply by gain, take the results, go through a dead time block, filter block to simulate a first order plus dead time type process, and we have the capability of adding in noise into our process. So that is how we are calculating then the simulated flow. Based upon that and our disturbance input, then we're calculating level. The level calculation is just an integration of the difference between the inlet flow and outlet flow of our tank, taking into account the period of execution and the size of our tank, which is represented by the gain. We limit the level to 0 to 100%. So again, you see it's very easy to implement that calculation in most DCSs. The calculated flow is immediately seen due to the wireless communication. To simulate window communication, then this is how we're doing that simulation of the window communication. The time since the last communication is monitored. If it exceeds the default time, then we allow the value of the transmitter to be communicated. Otherwise, we only communicate the value on the period that is set in the windowed communication, and only then if the value has exceeded the change that is indicated by the deadband. So the deadband, the period, and the default time then are used to simulate then the windowed communication. So both the level and the flow are calculated in that way. Let's look at the level control that is dictating the on-off valve position that we're using in our simulation. We'll also be looking at the control that is dictating then our valve position of their throttling valve that is used to calculate our level and our flow out of the process. So first let's look at the on-off valve control. We're looking at the wireless measurement here, going through our control that is dictating our output. To look at how we have implemented the control using the wireless measurement and the wireless on-off valve, we'll look at the control calculation. In the composite that is used for the control, there's a determination of whether the downstream block is in the correct mode. If it is, then if the block is in manual mode, then the operator can determine the output. Otherwise, in automatic mode, we look at whether the output is active. If it is and we're below target, then we remain active. If it is above target, then we turn off the on-off valve. If we're inactive, then we only turn the valve back on to the on state if the measurement has deviated below set point by the value determined by the deviation parameter. So this calculation of the discrete control can be very easily done in most DCSs. This is the online operation showing this, and as you can see in this case we have set point of 50. As long as the level measurement is above 50, then the discrete is turned off, so our on-off valve is turned off. Only when the level drops by more than the deviation limit, which would be 5%, do we then turn the valve back on. This is showing the pump out flow control. In this case, we're adjusting a throttling valve based upon the wireless flow measurement. The PID is set up to have PID plus capability, so it knows how to handle then our wireless measurement and to automatically handle the long time periods between measurement updates. And that is then used in adjusting the output. Here we see the online operation. It's better looked at by examining the trend. Here we're exactly on set point in terms of our pump out flow. We notice below the indication of the wireless measurement. You notice it's only communicated over 16 seconds. When we drop below more than the deviation limit, then the on-off valve is open as indicated by the green bars at the bottom of our trend here. To demonstrate the impact that the pump out flow has on the regulation of our on-off valve, we'll reduce the outlet flow by 10%. As you can see, when we do that, we get an immediate change in the throttling valve, the wired throttling valve, but the wireless flow measurement doesn't immediately reflect that change due to the fact that we're using window communication with an update period of only 16 seconds. We can better examine its impact by looking at a trend. As you notice here, we've changed the set point, but only when we get a new communication do we take further action after that initial set point change. But as you can see here, we very quickly come to target with our wireless communication. The impact on the level is shown through our simulation, and the on-off valve regulation of the makeup flow is directly impacted by the pump-out flow, as you can see here. As a result of reducing the pump-out flow, the level decreases much slower. We're taking less out, and therefore we only take the level is reduced more gradually. What we see is that it takes less time then to go from our deviation of 5% below level up to target due to the reduced pump out flow. We can examine the impact of the recycle flow on the control and how often the on-off valve has to be regulated to maintain level within the deviation limit. In this case, we have reduced the recycle flow by 10%, and there is an immediate impact upon the level, but this is better seen by looking at the trend. As you can see here, when we reduce the recycle flow, in this case we have to now make up more since less is coming into our tank, and therefore the on-off valve has to be on for a longer period of time to bring us back up to level. And so we see that here in our trend immediately. When we have the valve turned off, then we again see that the level drops much faster due to the fact that we don't have as much makeup flow coming into our tank. The time between the on-off valve going closed and open is now also reduced. So through our simulation, we can explore the impact of the process operating conditions upon the frequency with which the valve will be opened and closed. We can examine the impact of wireless on the tank level control, and examine then our implementation of discrete control. So we hope this example of how simulation can be used has been helpful to you in seeing how this can be implemented in your DCS system to verify and check out wireless control.